You want to hear about flex it, not on flex. It's so much stronger with burgers, pizza, brownies.
Well, they just, this morning, she put a new, like, Scentsy thing over there, and it is just flooding the hallway and the rooms with this. I think it smells okay. I think it smells okay, but it's really strong.
Yes, I'm not even tired. It's not like I'm going to the gym.
All right, page 140. We're going to look at example A that we finished yesterday, because I looked at it a little bit more and realized what I had overlooked, because Eric had a question about it, and I realized what I had overlooked about it. When we got to the part where it was x minus 5 to the n over 2 to the n plus 1, for that part, whenever you had that limit going to infinity, we kind of became fused at that part, but after looking back, I realized x we treat as what in this case? As a constant. So we have a constant here and a constant here. We have n to what power here? And n to what power here? So when you're taking the limit, if you have n to the same power, how do you find the limit? The leading coefficient. So the leading coefficient is x minus 5 and 2. That's how we get x minus 5 and 2 in that next step. It was the leading coefficient, because we have to remember x is a constant. So that's how that came about. Does that make more sense now, Eric, on that problem? Okay. Any other questions about that example we did yesterday? All right, let's look at example B. You do have a question?
I still don't understand what it's telling us. Like,
all right.
I don't have any problem with like the math and the calculations, but like, why do we do those calculations?
So
what is it giving us?
that's the part that's kind of hard to understand, and from some of the stuff I've looked at online, for this problem here, we're finding some interval that it represents some other function. In this case, we don't know what that function is. Again, these examples, we're not sure what function it's representing. They're not telling us what it's representing. Up here, we knew we were representing e to the x. Or if we do a problem, sine of x, cosine of x, those ones that we have memorized, those ones we know what they're representing. We're doing the same math as we would for like e to the x, where we know what we're representing, but in this case, we don't know what that original function is that we're trying to represent or trying to find the exact values of. Okay, so we're saying whatever that is representing, though, we're finding that interval. Within that interval, whatever that function is we're representing, it's exactly the same within that interval. Okay, so that's what we're saying.
But how do we know if it's exactly the same if we don't know what interval we're finding? Like, if we don't know what function we're
That's a good question.
That's what I don't know. Like
That's something I would have to look more into. That's something I would have to look more into. Okay, so I'll see what I can figure out and get back to you on that. Okay. All right, let's look at example B. For example B, can we tell what the center is? Yes, there's nothing that's added or subtracted to the x. So we know the center is going to be at 0. And we said we need to use what test most often for these two? Yeah, ratio test. So let's go ahead. We're going to do the limit. N goes to infinity. Absolute value. Again, we have the original, but everywhere we have an n, we put an n plus 1. So x divided by 3, n plus 1. We have x over 3 to the n plus 1 and x over 3 to the n. What are we left with? Think about your exponents. What are we going to be left with? X over 3 to the n plus 1 and x over 3 to the n.
X over 3.
Yeah, we have the n here and the n here, so we're just going to be left with 1x over 3. And when we're taking that limit, what do we want that to be less than?
1.
We want it to be less than 1. But again, we want this to be x, some x value less than. So how do we get x by itself? Yep, multiply by 3. So we're saying that x should be less than the value of 3. So when we get the absolute value of x equal to or less than some value now, this is what we're saying just as yesterday. This is our radius. So our radius of convergence is equal to 3. So yesterday we had drawn that little number line for that example, said we could go 2 units to the right, 2 units to the left. In this example, we can go 3 units to the right, 3 units to the left. But again, we're going 3 units left to right from our center. So where is our center at? 0. So we can go anywhere. Again, remember for the interval, we don't know our endpoints yet. So it's -3 to 3, but we're putting parentheses and brackets because we don't know about the endpoints yet. And then we have to test each endpoint. So we're going to test x equals -3. So -3, go ahead, Aaron.
I have a question. And then you guys say one. But how did you get, so I get that you found the radius of convergence for that, but you did it differently than you did in the last problem. Can you explain why? Like the last problem you solved, and then you solved, like, you had your radius equal to, oh, okay, you just said the equation. Never mind.
You're okay?
Yeah, I confused myself.
Okay.
I just had poor name.
All right, so we're going to test -3 first. If you plug that into the original and simplify a little bit, that would be like -1 to the n. So does that diverge or converge? -1 to the n. You could think of it as alternating. I think you could think of that one as nth term test too. Converge or diverge? Is it ever going to some value? Converging to some value? No, then it must be diverging. Okay, let's test x equals 3, which that reduced form would be 1 to the n. So 1 to the nth power, diverge or converge? I think if we look back at our nth term test, what does our nth term test tell us? I think by the nth term test it diverges. What does the nth term test say again? Can you remind everyone?
Whenever it doesn't equal 0, it diverges.
Yeah, when the limit's not equal to 0, so this diverges. If it is equal to 0, then it's inconclusive. So we tested our endpoints. So our final interval has to be what? Final interval.
Open on both sides.
Yep. -3 to 3, and it's an open interval. All right, any questions on this one, Eric? Anybody still copying? All right, let's go ahead to the next page. So this is that page I was referring to before we started. We have the 4 examples on the bottom. We'll go back to at a later time to review or practice. We're going to focus on the top 2 today. So C. We have the summation there of -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. What about our center? Okay. What do we think the center is? 0. Nothing is added or subtracted to that x value. If it was like x minus 1 and then to the power, that's when you would have a different center. But there's nothing added or subtracted. So now we can do our ratio test. When we're taking the absolute value, does the alternator matter? No, so you can leave that -1 to the n out when you're taking the absolute value. It doesn't really matter. So we would have, let's see, when we have x to the 2n plus 1 and you change it to n plus 1, what is our new exponent?
2n plus
2n plus what?
3.
2n plus 3. Anybody not sure how we got that? 2n plus 3. If I change the n plus 1, you have to distribute the 2, then you can add the 1. Okay, so x to the 2n plus 3 over 2n plus 3. Same reasoning on the bottom. And again, we're going to multiply by the reciprocal, so 2n plus 1. X to the 2n plus 1. Now is when, like yesterday's example, we need to see if we can cancel anything. What cancels? What are we left with? Does anything cancel? Look at the x to the 2n plus 3 first. Let's focus on one term at a time. Do we have a term that's similar on the bottom? Yes, this x to the 2n plus 1. So if we have similar terms here, how do we think those are going to reduce? What are we going to be left with? X to what power? X squared. The two n's go away. And then we have the 3 and the 1. Well, that's just going to leave you with x squared. Okay? Now we have a 2n plus 1 factorial and a 2n plus 3 factorial. Those are similar. But how are we actually going to write that or cancel that out? Is there a way we can rewrite the bottom to make it look like the top one? Eric, you say yes. Did you figure out how to yet?
Yeah, I think you write it 2n plus 3 times 2n plus 2 times 2n plus 1 factorial.
Exactly. You just reduce it by 1 each time. So you would have 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. Well, that 2n plus 1 factorial, that's going to cancel out. So you're just going to be left with the 2n plus 3 times the 2n plus 2. Does that make sense? I know I didn't write down all the steps, but are we okay with how we got from there to there? Okay. Now, that's the reduced form. We want to take the limit of it. Again, x is treated as a constant. If you take the limit, it's equal to what? As n goes to infinity. 0. We want the limit to be less than what?
1.
We want it to be less than 1. It is. So it's telling us it's convergent on all reals. So our radius has to be what? Remember, we had 3. Yesterday's notes, if you look back, I think there were 3 options for the radius. Yeah, go ahead.
How did we get like the one that equals 0? Because like what if you distribute the 2n and you get 4n squared?
Okay, you have 4n squared on the bottom, but you have x squared on the top. X is a constant. So it's a constant over some n value going to infinity. Yeah, you have to think of x as a constant. If you want to even write that down as a note, think of x as a constant in this problem. So the radius has to be what for this problem? Since it's convergent on all reals, the radius of convergence? Infinity. So the interval has to go from negative infinity to positive infinity, and no need to test endpoints. Those ones are nicer. Less work. I didn't even notice Eric must have been a little warm because I'm sure he's the one that opened all the windows. It's coming over from the room across the hall.
Oh, really?
Yeah, they put a new, like, Scentsy smelling dish thing over there today.
Was Kaminsky, yeah, she
Yeah.
said because her freshman stayed
Yeah.
Makes it easier for them to do.
All right, so that's it for part C. Any questions, Eric? No?
Nope.
All right, let's go to letter D. All right, the center this time is what? 3. Let's go ahead. I'm going to erase, so I have room. We're going to do our ratio test. So we change the n's to n plus 1, and we divide by the original. And once again, we need to determine if anything cancels out. I think stuff will. What will the answer be when you cancel out? What are you left with, top and bottom?
On the top, you'll have n plus 1. And also x minus 3. And it'll all be over 1.
N plus 1, x minus 3, all over 1. Again, if you think about the test we're doing, we're taking the limit as n goes to infinity. So your limit is what? Infinity. We want it to be less than 1. Is that true? No, that's not true. Do we have a, or what is, or do we have a radius of convergence? No. So if we don't have a radius of convergence, if you're not sure, look back at those 3 roles we had yesterday. What do we know is true if we don't have a radius of convergence? What do we know about it converging?
Radius is 0.
Okay, the radius is 0. Refer back up to that part 1.
Converges only at C.
Yeah, C, and C is your value of your center. So we do not have a radius of convergence. So do not have radius of convergence. So only converges at center. So if they wanted you to list this out, if it was like an open-ended question, you would say your radius is equal to 0. And if they asked you for an interval, there's really no interval, but if they ask it to be set as an interval, it would just be 3. That's your center. That's the only place it converges. Because we said we have no radius of convergence. The only place it's exactly the same is right at the center. So we've seen a few different types. The first one we had one endpoint that worked, one that didn't. The second problem we had 2 endpoints that diverged. The third one we had the radius of infinity. And then the fourth one we had a radius of 0. So we've seen a little bit of everything. Do we have any questions before we go on to the next page? So again, the next 4 examples, we'll come back to those and we'll practice with those later on. They're going to be more of what we were doing today. All right, let's go then. 142. So we're going to look at something that should be very familiar. It should be something that you should have memorized, and you have it on a note card somewhere, from very similar from 3.3. So we're now going to look at the special family of power series for which you practically already acquainted, the Taylor and Maclaurin series. So the Taylor series, we know where x is equal to c, or centered at x equals c. Maclaurin is just when it's equal to 0. So this is of the same form that we used in 3.3. But what do we notice? Well, there's really 2 things here that are different. two things that are different from what we had in 3.3. Two things directly associated with that formula. Okay, that's important. We have an equal sign now. We did not have an equal sign before. We were approximating. So now we know in the problems we've been doing, we're talking about when it's exactly equal to something, not when it's an approximation. So in relation to that equal sign, what's different that causes it to be an equal sign and not an approximation? What do you notice with that formula? Yeah, we have it written out to the nth term here, but then we also still have the plus dot 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 because we're taking this into infinity. If we take any series and take it to infinity, it's going to be the exact formula of what we're representing. So like we said in 3.3 with like e to the x or sine of x, when we had that Taylor polynomial, we would stop at certain degrees, 5th degree, 6th degree, 9th degree, depending on the equation, we would stop at a different degree. That's why it was an approximation. When we're talking about these series now, the Taylor series, this dot dot dot's important because it's going to infinity. So we're talking about the exact. That's why it's equal to, not an approximation. So down below it even says, notice how we use an equal sign instead of an approximation sign. Do you know why? Well, that's exactly what we were just talking about, because we're going to the nth term. We're going to the nth term. All right, so example 3, it wants us to find the Taylor series for f of x where it's equal to e to the 5x, centered at c equals 2. Give the first 4 non-zero terms and the general term. So they're saying we would need to write it out like up here, the first general 4 terms, then the first 4 non-zero terms, and then the general term. So this is considered the general term. This is what they want listed. So we're actually representing the entire series. So we know the center's at 2, and when they give us the function, so let's just start out writing the original. F of x is equal to e to the 5x. If we think about our center, what is this evaluated at 2? We get e to the what? E to the 10th power. Okay. And they say 4 non-zero terms. So how many more derivatives do we need to take? Yeah. Well, we need to take, if we're going to the 4th term, this one counts as our first term. So we need to take 3 derivatives. So f prime of x, again, very similar to what we did in the last section. Remember, it's itself times the power of the exponent, so 5e to the 5x. Evaluated at the center is 5e to the 10th. I'm just doing both steps at once, finding the derivatives and evaluating them. Second derivative. This can be written 2 different ways. What do you get when you get the second derivative? Yeah, we'll write it that way. 25 e to the 5x. You'll see a pattern in the next one if you didn't catch it yet. And then if you don't, we'll talk about it. Because that pattern will come about in the final answer too. Okay, then we get 25 e to the 10th. Third derivative. What do you get for the third derivative? 125 e to the 5x. So that equals 125 e to the 10th. So we have our first four terms. So they want us to write the Taylor polynomial now for e to the 5x. First four non-zero terms, then the general term. Well, the first term is just e to the 10th. Remember, referring to the Taylor series or Taylor polynomial, these values represent what in the Taylor series or Taylor polynomial? What are these values that we found? What are they representative of? Yeah, the coefficients within them. So we have e to the 10th plus 5e to the 10th times x. And what's with the x? Try to think back to your polynomials. Yeah, the center, so it should be x minus what?
0 or 2.
Yeah, in this case it's 2. Okay, so that's the first two terms. Third term, 25 e to the 10th x minus 2 squared all over 2 factorial. That's a third term. Fourth term, 125 e to the 10th x minus 2 cubed all over 3 factorial. So those are the first four terms. Then we're going to have dot, dot, dot. We need to come up with our general term. And then again, this is a series, so we have to have our dot, dot, dot general term plus dot, dot, dot because we're going to infinity. So what would the general term of e to the 5x be? General term of e to the 5x. Look at your similarities between the first four parts. How can we create a general term? Or if you don't know the whole thing, do you know at least a piece of it?
What do you mean general term? Like the formula that gives you each thing?
Yes.
It's just 5 to the times
E to the what?
5x.
In terms of this specific example, it's e to the 10th. Yep. And then what?
Times x.
To what?
Oh, to the
Over n factorial plus dot, dot, dot. So, as we see, this is the general form for this e to the 5x, so it's important to notice here. Since we created all these coefficients from e to the 5x, this can't be used for any other e. It has to be used for the e centered at 2 because they're going to change. These all coefficients are evaluated when the center is 2. So if your center changes, you have to find a new series. The series only works when this is centered at 2. So if they have another question and ask about the center being at 1 or the center being at 0, you have to find a different series now because remember, these coefficients were found with the center being at 2. Okay? And if it's at 1 or 0, each coefficient would now be different. All right, so before we move on, that is all they asked for that example. We found the Taylor series. That's it right there. We found the general form, 4 terms, and that's it. Before we go on to the next section, I kind of want to review a few terms before we get started with that. And that's probably where we're going to have to end for the day. So I'm going to include them here. If you still have space here, this is where you should include them. I'm going to erase a little bit so I have room to write these. So there are 3, and we're going to look at the 4th one too. Probably going to be tomorrow now, but the 3 they have listed there. E to the x, sine to the x, and cosine of x. Again, these are ones I told you should have memorized, so I want to review them now, and we should write down the form so we can keep those in our memory bank. So we should have those memorized. But if you need to look back as a refresher quickly, what is the Taylor polynomial for e to the x?
Just the one that's like 1 plus x squared
So it's of the form x to the n over n factorial. Very good. That's e to the x. And then you should have sine of x. Also memorized, Taylor polynomial.
X plus x cubed. I thought this cosine one was
You could do the cosine one. We found the sine, and then we found cosine from sine. Which one do you want to do, cosine or sine?
I don't know, which one is negative first? Because I thought that the cosine one was. Is it not?
They both have a minus sign.
Really?
Yeah.
Oh, I didn't know that. So, we'll just do sine still.
So we have x minus,
X cubed over 3 factorial, and then plus x to the 5th over 5 factorial.
and we'll then from there on it's just going to change back and forth. We have the alternator, negative 1 to the nth. X to the 2n plus 1 over 2n plus 1 factorial. So that was for sine of x. And then we said from sine of x you can find the cosine of x. So what would the cosine of x formula be? Taylor polynomial. Remember, we found a way to find cosine of x from sine of x. Go ahead.
It's just 1 minus x squared over 2 factorial minus, or yeah, plus x to the 4th factorial.
So we have the alternator again, negative 1 to the nth. I'm going to run out of room here, but we have x to the 2n all over 2n factorial. So again, those are just a refresher. Those are 3 that we should try to put in our memory bank and should try to remember. And tomorrow, we'll start right here with these 3. So these are 3 that you have memorized. We're going to look at this 4th one here, and we're going to write down the series for this one. And that's another one that you should have in your memory bank. And we'll go on from there with more examples.